Okay, let's unpack this. We often talk about automotive disruption, looking at the big global players or maybe those flashy startups.
Right.
But today, we're zooming in somewhere different, Central Europe. We're looking at a really critical place, the Institute of Automotive and Transport Engineering, or IAE, in the Czech Republic.
Yeah, this is really where the rubber meets the road, that intersection of academic thinking and actual industry application.
Hmm.
The IAE, it's led by Professor Josef Schutina, and their whole focus is summed up nicely. Innovative technologies for smart, low-emission mobilities.
Smart, low-emission mobilities. Okay.
And this isn't just theory, it's not just papers. They are engineering the future of transport, really, from the ground up.
So our mission today is to figure out how they actually do that. How does a major European center like this balance everything?
Exactly.
We've got some great source material detailing their unique structure, how much they rely on industry partners, and some really cutting-edge projects.
Things like hydrogen, digital twins, AI, that's all in there.
It really sounds like the blueprint for training the next generation of engineers and pioneering the tech itself.
It really is. Think of it like a vertically integrated knowledge pipeline, from education right through to industry.
Okay, so the first thing that really strikes you is just the size and importance of the IAE.
Oh, yeah.
Our sources say it's the biggest, the most recognized automotive institute in the whole Czech Republic.
That's right. And they're currently educating, I think, over 180 master's students, people studying things like automotive mechatronics. Serious stuff.
And they operate under this clear philosophy, these three pillars you mentioned.
Yeah. Education research industry. Simple but powerful.
But the really interesting part, maybe, is how deeply connected that industry pillar is to the money, the funding.
Absolutely critical. If you look at their funding structure, it tells a big story.
Go on.
Well, you've got research projects bringing in about 38%. Education support is around 32%.
Okay, standard enough for an institute.
But then a huge 30% of their budget comes directly from industry cooperation.
30%, just straight from companies.
Straight from industry. And that's not just, a small donation here and there. That level of funding means they're producing results that manufacturers actually need, like right now.
Wow. That's a massive vote of confidence, isn't it?
It really is. And if you drill down into who is providing that 30%, well, it's dominated by one major player.
Let me guess. Skoda Auto. Given they're Czech.
You got it. Skoda Auto contributes a massive 45.6% of that industrial funding. Almost half of the industry money comes from them.
45.6% from just one company. Now, that does raise a question for me.
Okay.
Is that healthy? Relying so heavily on Skoda. What if Skoda's priorities shift? Could that put their independent research at risk?
It's a fair point. It's definitely something to consider. But the way it seems to work is more symbiotic.
How so?
Well, that deep integration means the research isn't happening in a vacuum. It's directly tied to real-world cars, real-world problems.
So speeds things up.
Immensely. Compared to relying only on, say, long government grant cycles, industry provides this almost real-time feedback loop.
Okay, I can see that. And it's not only Skoda, right? There are others.
That's right. While Skoda's the biggest, you also see Continental Barum chipping in about 16.1% and Garrett Motion with around 11.2%.
So several key players involved.
Yeah, and that heavy industry involvement basically guarantees that their core areas, automotive design, powertrains, vehicle dynamics, stay super relevant to what manufacturers actually need today.
Okay, so we've established the structure, a powerful base, really tightly linked with industry money.
Yep, the foundation's solid.
So let's look under the hood, as you might say. What are the big bets? What are they actually researching for the future?
They're covering a lot of ground strategically. On the powertrain side, there's a clear focus on alternative fuels.
Hydrogen.
Exactly. Hydrogen engines and combustion specifically. But they're also working heavily on hybrid and electric powertrains at the same time, covering the bases.
Makes sense. But it's not just about what makes the car go, is it?
Not at all. They're investing just as heavily in how the car drives, how it interacts with the world, so ADS.
Advanced Driver Assistance Systems.
Right. And looking towards full autonomous driving capabilities, too.
And the piece that ties all these complex systems together.
That would be digital twins and system simulation. You absolutely need that virtual layer.
Yeah, you can't manage the sheer complexity of a modern, low-emission, semi-autonomous car without really robust virtual testing. It lets you iterate so much faster.
Precisely. And they even have a dedicated area for NVH testing.
Noise, vibration, and roughness,
Mm.
making sure the efficient car is also pleasant to be in.
Exactly. Efficiency and, well, refinement have to go hand in hand.
So all these research threads, do they come together in any specific big projects?
They do. Their flagship initiative right now is called the ITEM project.
ITAL.
Stands for Innovative Technologies for Smart Low-Emission Mobility. It's running from 2024 to 2026 with a budget of about €5 million.
€5 million.
Wow.
And focused on,
Focused squarely on those key areas: hydrogen, electromobility, ADS, autonomous driving, and, crucially, those digital twins we mentioned.
okay, so that 5 million signifies they're really leading the charge nationally, not just doing isolated research.
Absolutely. That project actually supports other national centers, too, like the Buchek Vehicle Engineering National Center of Competence and the National Hydrogen Mobility Center.
So they're not just part of this shift to low-emission transport in the Czech Republic.
They're helping define the technological paths for the whole country. It's quite significant.
Right. Here's where it gets really interesting for me.
Yeah.
Let's dive into these digital twins. How do they actually work? Because this sounds like more than just, basic computer modeling.
Oh, it is. It's a very sophisticated setup. Think of it as a high-definition, closed-loop system that blends the virtual world with the real physical world.
Okay. How? What tools are they using?
They're using the pro stuff, the industry standards, things like IPG CarMaker, GT Suite, and the whole MathWorks suite, MATLAB, Simulink, Roadrunner.
So tools that any global car maker would recognize and use.
Exactly. That means their simulations, their findings are immediately transferable, immediately usable.
Okay, so they've got the virtual tools. But how do they connect that virtual world to an actual car, a physical test vehicle?
That's the clever part. They create this constant feedback loop. They'll take a real car, the source mentions a Skoda Enyaq prototype, an electric SUV,
All right.
and they essentially plug it into their system. It runs alongside a virtual vehicle in a whole virtual city. They even use tools like SUMO for realistic traffic simulation around the virtual car.
So the real car's data affects the virtual world, and maybe vice versa.
Precisely. Data is constantly flowing back and forth between the physical Enyaq and the high-performance computers running the simulation. They use robust CAN bus transfer systems, even mentioning Vodafone for connectivity.
And the amount of data they're pulling from that real car,
Yeah.
this number blew me away.
It's astonishing, isn't it? They use specialized data loggers from Vector and Imicly, and the system is set up to measure, get this, 25,000 variables
25,000 simultaneously.
at any given time. Yeah. Just think about that. Decades ago, engineers were thrilled to log maybe 10 channels reliably.
It's a different world. What kind of variables are we talking about?
Everything. The really granular stuff needed for modern EVs and ADAS, they're pulling EV motor torque directly off the CAN bus, lateral acceleration when ABS or ESP kicks in.
But it goes beyond just vehicle dynamics, right? I saw something about comfort.
Yes! That level of detail is amazing. They're logging the comfort CAN data, too. Things like the cabin temperature, the outside ambient temperature, even the exact position of the HVAC flaps.
Why log the flap position?
Because it lets them build incredibly detailed energy consumption models. They can chart exactly how much energy the Enyaq uses, not just to drive, but to keep the driver comfortable, warm in winter, cool in summer. It all adds up, especially for EV range.
That makes perfect sense. Okay, so this massive data set, 25,000 variables.
Yeah.
That must be the bedrock for their vehicle dynamics work.
Absolutely. It fuels everything. They run standard simulations, of course, parametric studies, but they also do something called inverse simulation.
Inverse simulation.
Yeah.
Okay, that sounds a bit academic. Can you break that down? What does it mean in practice?
Think of it like working backwards. They take the data from a real-world test drive, maybe a hard corner, an emergency brake, something dynamic.
Right.
And they feed those results back into the virtual model. They essentially force the simulation to replicate what actually happened to the physical car.
So it's a way of validating the digital twin, making sure the math truly matches the metal.
Exactly. Does the virtual car behave identically to the real one under the same forces? It's a crucial step to ensure your digital twin is actually trustworthy.
That validation loop seems key. And they're applying that rigor to components too, right? Like tires?
Yes, they understand that the simulation is only as good as its inputs. Tires are notoriously complex, so they're developing a special towed platform just for tire testing.
A physical rig.
A physical rig, yeah. Still in development, according to the source. But the goal is to use it with what they call an inverse multi-body system model, basically, advanced math, to accurately estimate those complex tire characteristics. Get the tire model wrong, and your whole vehicle dynamics simulation is off.
Makes sense. Get the foundation right. And this close industry tie-in, especially with Skoda, it's already yielding results, isn't it? There was something about aerodynamics.
Yes, a really concrete success story. Their collaboration led to an innovative patent, something that actually reduced the vehicle's aerodynamic drag coefficient, the CX value, by 4%.
4% might not sound huge, but in automotive terms, especially for EVs, where range is king.
It's significant. That's real efficiency gain, real energy savings, potentially across millions of cars. It's not just theory, it's on the road.
Okay, now this brings us to maybe the most future-forward application of all this data, artificial intelligence.
Right. This is where you see the shift from just loading cars with sensors to making cars genuinely intelligent with data.
How are they using AI specifically?
Their focus seems to be on using AI to make sensing smarter and maybe even cheaper, overcoming the limitations of physical sensors.
So instead of adding another expensive complex sensor to measure something tricky,
They train an AI model to estimate it accurately using data from other, perhaps simpler or already existing sensors.
clever. What kind of tricky variables are we talking about?
A key example they give is tire side slip angle. Hugely important for stability control and autonomous driving, but traditionally very difficult and expensive to measure directly on a production car.
So how does the AI estimate it?
They use a hybrid approach. They combine classic physics-based models, things called Leuenberger or Kalman observers, which understand the basic vehicle dynamics
Yeah.
with modern neural networks, specifically LSTM and GRU types, which are good at understanding sequences and time series data.
So the physics model gives the AI a starting point, and the neural network learns the nuances from all that other data, the other 24,999 variables.
That's the idea. The AI learns the complex correlations and effectively fills in the gaps where a direct sensor is missing or too costly. It's proving that software intelligence can potentially replace expensive hardware.
That has huge implications. And they're putting this into practice, building actual systems.
Yeah, the final stage seems to be integration. They mentioned developing a driver monitoring system using multiple cameras, 3 inside, 1 in the mirror, plus dashboard cameras, all feeding into intelligent systems.
And verifying existing systems, too, like traffic sign recognition, making sure the car sees the world correctly for ADS and autonomy.
Exactly, ensuring reliability.
Right.
And that NVH work we mentioned earlier, noise, vibration, harshness.
Yeah.
That also uses a combined approach. Real-world experimental testing modal analysis, field tests, feeds directly into their computational models like finite element method, FMM, and multi-body simulations.
And not just for cars.
No, they apply it broadly. The source shows an example of modeling a heavy tractor, the body, transmission, cabin, to analyze vibrations and improve comfort for the operator. It's about the whole mobility ecosystem, efficiency, safety, and quality across the board. Hashtags, tag, out at outro. So if we synthesize all this, what we're seeing at the IAE is more than just a university department. It really is this critical knowledge hub.
Yeah.
And it's powered by this really smart strategic model that tightly integrates education, very rigorous testing, both virtual and physical, and these absolutely crucial industry partnerships. That 30% industry funding, heavily leaning on Skoda, is key.
It lets them move incredibly fast, doesn't it? Generating just mind-boggling amounts of data. That 25,000 variable number sticks with me, and then using all that real-world input to train intelligent AI systems.
Exactly. And that speed, combined with tangible outputs like the Aero patent or their work on advanced EV prototypes, it just confirms that the future of mobility, low emission, increasingly autonomous, is being actively engineered right now in places like this.
Places maybe not everyone thinks of first.
Right. So what does this all mean for you listening? I think this model points to a major shift in engineering.
Which is?
That the most efficient, the most scalable systems moving forward will be the ones that cleverly use AI and advanced algorithms to estimate the things that are hardest or most expensive to physically measure.
Software replacing hardware, in a sense.
In a very intelligent sense. So if AI can reliably figure out something complex, like tire side slip using cheaper existing sensors, well, the provocative thought is, what current, complex, expensive measurement tools that engineers rely on today might become obsolete tomorrow, replaced by smarter software?
What gets estimated away? That's a fascinating question. The era of intelligent estimation is definitely dawning.
It seems to be.
Something to chew on. Well, that's our deep dive for today. Thanks for joining us.